Um, so I just wanted to this is important announcement. So the final exam is at 6 p.m. to 8 p.m. on Friday, May 9th. It's in this room. There's not going to be any lecture on that day because it's already the study period. So it's going to be in this room, and we'll be checking IDs. So make sure you bring your ID, student ID or driver license, whatever, passport, whatever that can validate your identity. And exam is 2 hours. Probably going to give you guys some leeway room. It's not going to be exact 8, but a few minutes after. So make sure you get it done. And also the lecture on May 2nd will not be recorded. So if you're here and the very last lecture will not be recorded because it's going to be a review. I'm going to do some examples and possibly so anyway, so that one is not recorded. So if you want to be here, you're welcome to do so. But if you don't want to be here, it's fine. There's no new contents to be covered that day. It's going to be a review. So after some investigation on the final exam, the format is going to look like this. Oh, you guys see it, yeah. So there are going to be 7 problems. You can do any one. There's no order. You can do any one first, any one second, and you don't have to submit one by one. You can submit them all at the end, or you can submit one by one, regardless you have to do it. But you submit all 7 problems before the clock, before the end time. It's going to show the time, 8:05, for example, 8:05. And if you pick any problem to do, and you finish that problem, you submit it, and you see a button saying, take it again. So if you did it wrong, if you didn't get 100% on that, you can redo it. And redo will give you a second chance, and the grade will be average. So for example, if it's one problem, like one multiple choice question, you did it wrong, you get a 0. You get it correct, you get 100%. But if you did it wrong the first time, you do the second time, you get 100%, and your average will be 50% of that problem. But if it's many multiple choice, like one of the problem, for example, has 10 questions. And then the first time, if you did all 10 correct, of course, you get 100%. But if let's say you get only 5 correct, the first time you get 50%, the first one. But if you're not happy, you can do it the second time. But if your second time you did 100% right, you get average 75%. But if your second time you did like everything was wrong, 0%, your average will be 25%. So you have to take a chance, right? But what it does is that it tells you which one. It doesn't tell you which one is incorrect, but it does tell you which one you answered. So you should write down, which one you answered. So the second round, you can try to correct the one that you don't do it. Yeah. You get average of 2 try. No, per problem, not per question, per problem. Section. Yeah. Look, 1 to 7, so 7 problems. Yeah. You got an average of each problem, not the sub problem, not for each sub question. So it's only for that bigger problem. Yeah. So the reason I give you a second chance because I'm saying, sometimes the problem was 10 points, and if you made a silly mistake, you lose all the points. So that's kind of not fair. In my opinion, it's not fair. So you can have a second chance. Oh, I made a silly mistake, so I will redo it, and I'll get it correct. But if you don't know how to do it, if you didn't make a silly mistake, it simply didn't know how to do it, your likelihood to get the second time right is also small because many of the problems will have like 7, 8 choices. So it's not like 2 choices, true and false. It's all like many different choices. If you, I know some of the answers doesn't make sense, so you can eliminate them right away. But if you don't know the problem, if you don't know how to do it, it's hard to like eliminate. You have to really do it. So any question on that? Yeah.
Did you say the problems are going to be pretty similar difficulty to the quiz?
It depends. Some problem may be easier, some problem may be more difficult. It's definitely not a copy of the quiz. Yeah. But it's all what we covered in classes. If if you're in class, if you listen to if you're in class, or if you watch the video, or if you did the homework, you did the problems, the examples in the book, if you feel like really fluent, you will get 100%, unless you make a silly mistake, but you have a second chance, right? So that's what I want to tell you. But I mean, if you don't follow, you don't do the problem, if you don't like read the book, if you don't come to the lectures, you don't listen to the video, you simply bet on something I don't know, your chance will be, fairly bad. So far, in our class, you look at the overall, I think as a distribution is pretty good. Get quite a few A's, and we get a lot of B's, C's, but we still have quite a few F's. And I'm worried about those. Yeah. Yeah, 2 attempts for each problem. Yeah. It's average, right? Yeah. Any question? Any other? No. Because under each problem, there might be one question or it might be 10. So it depends on the, some of them are broken down to like smaller small questions, but some of them maybe just, just one question that you have to do some manipulation and then fill up the answer. Okay. Yes. Yeah. You can use your notebook. Yeah, no problem. Yeah, same as the quizzes. Yeah. If you need TAC support, you should schedule with them early on so that you can get the time slots you need. Because you shouldn't be taking that after like 6 p.m. On that day. So it should be you should be taking it earlier on that day. Okay. Any other questions? Okay. The two here. Okay, I didn't see on this. Yeah, go ahead. Make it due on Monday. What I have to do, my TA has to have time to grade them. He has a lot of work to do, so it's hard for me to change it. I can possibly change it to Sunday, like 1 day later. Is it Saturday? I can change to Sunday, but Sunday night. Okay. Anything else? Another question here. Okay, so if not, then we're going to continue on chapter 11 feedback, and our next quiz is based on feedback control. What we covered today is going to be on the quiz of next week. Okay, so last week we got this little head start on this chapter. Basically, when you have a feedback, there are a couple of things we talk about. Like A is open loop gain, and beta is the feedback factor, and XF is the feedback signal, XS is the input, and XI is the error between input and feedback, and XO is output. So if you take all these mathematic relations between all the variables, we can easily get like XO is, for example, A times XI, and XI equal to XS minus SF, and XF equal to beta times XO. And all the way we plug in those 3 numbers, we found eventually the closed loop gain is AF, which is XO over XS, which is A over 1 plus beta A. So very simple equation. And because what happened, A is really typically pretty big, like in the thousands, and beta is feedback factor, it can be anywhere between 0 and 1, but it's not going to be 0, because if it's 0, it's no feedback. So it's between 0 and 1. So therefore, this number typically is much smaller than A. And often it's so small that we can basically, if we neglect this 1, so beta times A is much larger than 1. So if we neglect this 1, we can see this A is going to cancel. So the closed loop gain is 1 over beta. So what we're saying that the closed loop gain is only related to beta. So if beta is less than 0.1, then you get gain is 1. If beta is 1, then your gain is 1. So that's how this works. But given this block diagram, it's sometimes it's hard to understand what really it is in terms of, say, a circuit. So therefore, before we get into circuit, we say sometimes we introduce another important concept. It's called loop gain. The loop gain means you break the feedback loop anywhere in the circuit, and you apply an input at the break point, and you measure the output at the other end of the point, and then you use the two to get the ratio of these two, you will get the loop gain. So loop gain is called beta A. For example, over here, we break over at that point, we apply XT, we get XR. Remember, at this point, we also set the input to be 0. But then we get this, see, whatever XT multiply beta, and then get to that point and multiply by A, and we got XT is beta times A times XT. So therefore, the loop gain is beta times A. This is very important because in the future, a lot of the times with the actual circuit, it's impossible to get A. So it's just not possible to get the actual A for that circuit. Therefore, we have to get beta A, and then we get beta. So we use beta A divided by beta, we get an A. So that's how we get it. So today, we're going to spend a lot of time on that. To illustrate how this works in the circuit, we talk about this op-amp loop. And in circuit theory, we know that for ideal op-amp, the gain is like infinity, and the input resistance also infinity, and therefore there's no current flowing there. Then we get this open circuit, and the gain is A times Vi. In this case, A is not infinity, but certain open loop gain. And then if you look at here, we see that because there's no current in this branch, so we all coming here, this R1, R2 becomes a voltage divider. So whatever the voltage over here is the VF is the voltage divided between R1 and R2. And we use Vs minus Vi, Vf, we got Vi, then we multiply that by A, we got Vi, times A, we got Vo, and then we plug in this back, we found Vo is R1 plus R2 over R1 times Vx. And so this is what we get for the loop. This is the closed loop gain. And then we can also write down, the loop gain, the feedback ratio, things like that. We can do that. So this says here, for example, we can find out that beta is R1 or R1 plus R2. Okay, so and the open loop gain is like this. Okay, so we do that. Now let's continue on to what we have had. The feedback loop gain of the feedback circuits has two initial advantages. Later on, we're going to discuss many more advantages, but here we're going to discuss two. So one, we're going to look at sensitivity. So what is sensitivity? Sensitivity means if you have A that changes to A plus delta A, let's say 20%. So for open loop, your gain, which means your VO, is A times V in. So it will be either A times V in, or it's going to be A plus delta A times V in. So if you look at this equation and say, well, if A changes 20%, my output changes 20%. That's how sensitive your output to your input. So whatever your input changes, the output is so sensitive that when your gain changes 20%, your output changes 20%. Now you might say, how come I gain change 20%? Well, we know that electronics are thermal based. Remember, we have thermal voltage, threshold voltage, all that stuff, right? Temperature rise can change your gain. And other parameter change, like R change, or your frequency is change. For example, if you have this capacitance that changes over temperature or something, that can introduce your circuit. At some point, it will shift your pole. So your frequency might fall not in the middle, but actually at the 3 dB point or somewhere over there. So your gain changes for that particular input, right? So which means this open loop is very sensitive in terms of parameter change of your circuit. So sometimes this is not good, because if my circuit changes, temperature rise from 25 degrees C to 125 degrees C, my gain might change 10% or even 20%, and then my output actually change 20% with input. So that's not good. But if you look at your closed loop gain, right, and then your output now is AF times V in, which means what happens if my A change 20%? Would my VO change also 20%? So well, you can plug in the numbers. You can plug in A plus delta A, then beta A plus delta A, and you can say, for example, here you can say we say A plus delta A, and here we say 1 plus beta A plus delta A, right? And then we can do what we can do is we can do this we can break this down to A over 1 plus beta A plus delta A, and then plus delta A over 1 plus beta A plus delta A. But still, this is not so clear. See what exactly how much if A changes 20%. If this is 20%, how much would that thing change? One of the approximations that okay, if this change is not so big, we can probably neglect this one. So this is approximately the same as this. But then we have this one. Okay, we have delta A. So again, we neglect this one, and then we see like this is going to be delta A over 1 plus beta A. Now, what happens if Y is small comparison to this one? So that's probably how we can do this real like interesting comparison. Is that we're going to have A divided by beta, A plus delta A here, and then plus delta A over 1 plus beta A plus delta A. So sorry, this is not. We're gonna A is small, so we're gonna neglect that A. So it's gonna be delta A over beta A plus delta A. And if we further neglect the delta A, if it's relatively smaller than A, or maybe not 20%, maybe 5%, whatever that number is going to be. So this is going to be A divided by beta A plus delta A over beta A. And then the first one is 1 over beta. This is idea. Okay, plus this delta A over A divided by beta. So you see, this delta A over A is a percentage change of the gain. And then this is our initial like idea gain. And this is idea gain, which means if delta A change like 20%, if without the feedback, we know that the output will change 20%. But with this feedback, but this is 20%, but this is again divided by A. So this is going to be further like reduce the whole closed loop gain. Now this is not a very useful way to compare. So maybe what we can do is to take the derivative, and then that way we can look at exactly how much gain we're going to get, how much change we will have. So let's say that we're going to take this feedback over dA. So we're going to say, okay, this typically you can say delta AF over delta A. So that's how we write it in math. And so that delta, we can use D. So D means derivative, so we take that thing with a derivative, which is d over dA, so 1 A over 1 plus beta A. We'll take this one. And if you know, remember how to take derivative of this number. So we take the top, dA over dA is 1, which is 1, and times the bottom, and then minus the bottom is dA is beta times A, and divided by the bottom is 1 plus beta A squared. And we further simplify this, the top actually cancels. So we got this one to be 1 plus beta A squared. Which means if we now take, we multiply this DAF all here actually, because this two, we're going to say delta AF over delta A equal to 1 plus beta A squared or 1. Now what we're going to do, we multiply delta on both sides so that we get delta AF. So delta AF equal to delta A over 1 plus beta A squared. So now we're going to do delta AF over AF to get the percentage, because delta is the absolute change. So often we like to know what exactly the percentage change. So now we're going to say this is going to be delta A over 1 plus beta A squared times 1 over AF. Okay, we know that AF is going to be A over 1 plus beta A, right? So this 1 plus beta A cancel. So we got delta A over A times 1 plus beta A. And you can see this percentage of change is equal to this percentage of change, but divided by 1 plus beta A. So because 1 plus beta A typically is quite big, so whatever A changes, like 5%, and it will be divided by a few hundred, and a few times of a few hundred. So basically, it really reduces the sensitivity, which if this change 20%, this is not 20%. This is actually much smaller number. That is divided by 1 over beta plus A. So that's what it means. So AF percentage change equal to A percentage change divided by 1 over beta A. So this is what we talk about sensitivity. And the other interesting property of a feedback control is the bandwidth property. Now, bandwidth, I just going to use maybe 1 or 2 examples to illustrate how bandwidth is going to change. Okay, suppose you have a gain which can be written as AM over 1 plus S over WH. And we can do this for the low frequency response as well. So this is the equation for the high frequency response. Remember, S over WH. So if this is AS, and we know that AF, S is going to be AS plus 1 over beta. So by the way, beta is usually not a complex, usually, but sometimes it could be, but usually not complex. So here we simply assume beta is a constant. But of course, beta can be a complex number in the future, you will see. But in this case, we're trying to illustrate that if beta is a constant, we're plugging AS into this equation, we'll get AF S equal to AM over 1 plus S over WH, and 1 plus beta times AM 1 plus S over WH. So what we're going to do is we're going to multiply 1 plus S over WH on both numerator and then denominator. So we'll get AM. On the top and bottom, we have 1 plus S over WH plus beta times AM. And this goes to AM over 1 plus beta AM plus S over WH. Now, in this case, because this case we have AM over there, we can divide both numerator and denominator by 1 plus beta AM. It will give you much better expression. You see what it is. So it's going to be AM divided by 1 plus beta AM, and then times 1 over, which can be 1 plus S over WH, 1 plus beta AM. So this is the final equation. You see what happens here is the middle band, right? So A over 1 plus beta A, that's the middle band again. Now what is this? This is a high frequency response, which initially was S over WH. Now it becomes S over WH times 1 plus beta AM. What does it mean? It means your high frequency pole has been increased from WH to this number. Now, typically, this is quite a large number. It's going to be like 100, 200, or maybe 500. So which means your WH has been increased by many times, not just 2 times, but it's going to be 10 times, 100 times, 500 times. So this is great because we actually increase our bandwidth. Of course, you can do the same thing for your low frequency pole. If you have low frequency pole, we can do, for example, it's going to be S over S plus WP. And again, we have this AFS going to be AS over 1 plus beta times AS, right? So then we have AFS, we plug in the number in here, we get S plus WP divided by 1 plus beta over S. There's AM here also. Don't forget this AM. S over S plus WP times AM. And again, we do the same thing. We multiply S plus WP on both sides. We'll get AM. Over here, we just leave it like that, times S. And then this is going to be S plus WP plus beta AM times S. We get that term. So now we are going to we're going to change that to AM S over. So this is going to be S 1 plus beta AM plus WP. Okay, so now we're going to divide both numerator and the denominator by AM. So we get AM over 1 plus beta AM. We divide both numerator and the denominator by 1 plus beta AM. Now we have S here. So here we are going to have S plus WP over 1 plus beta AM. If you look at, interesting, this is the middle band again, and this is the low frequency response. If you look at the pole frequency, what happened? It reduced by 1 plus beta AM. So this omega P F is going to be omega P over 1 plus beta AM, which is much smaller than the initial pole. And of course, if we go back here, we see this WHF becomes WH times 1 plus beta M. So you can see the low frequency pole by moved even lower, the high frequency pole is moved up even higher, which means your bandwidth now is increased a lot. It depends on the beta, on the value of beta times A. If we do a body plot, we can plot like this. This initial, the black line is the initial, like open loop, and here the other one is like the bottom. The other line, this line that's called blue line here, is your closed loop. Now you will see here, one of the things is clear that this open loop, this closed loop gain, A, like F middle is equal to AM over 1 plus beta M. So, and then now we can say, okay, W pole is equal to F equal to WP divided by 1 plus beta times N, and this WH, F equal to WH times 1 plus beta times N. So, but when the bandwidth is increased, the downside that your gain also decrease. So instead of like 5,000, now you might have 500 or even less, maybe 10. So in some examples to follow today, we'll see some of the gains will actually maybe just like 10 or maybe even 5, right? So your middle band gain significantly drop, but you do get the the benefits of opening up your bandwidth. So if you wanted to further, like if you say, okay, I do need a very large gain. Now this feedback, kill my gain. What do I do? Well, you can have multi-stage. You can have like one stage and then you have another stage, and you can have a smaller feedback gain, like a better, smaller, and you have a much better closed loop gain, but you still open up the bandwidth. So this is very important. In feedback, there is a so-called voltage feedback. There's current feedback. So we're going to discuss all of this type of feedback. Now think about if input side is voltage, output side is voltage, right? This is called voltage feedback. But if input is current, output is voltage, we call it's voltage feedback becomes current. So so it's hard to call them. So we call like transconductance. But in fact, in the future, we're going to call them shunt, or series shunt. So shunt means parallel. So instead of like call them a voltage feedback or current feedback, we'll call them a shunt. We call them series. Then if primary is series, secondary is parallel, we call them series parallel. So this is exactly what we see. See, at the input side, the feedback is in series with the input. The feedback is in series input, so we call it series. But on the output side, you can see our feedback input is in parallel with our output, right? So this is called series parallel. But in the future, you will see, well, we can change. We change input to series as well, output in series as well. You have series, or you have parallel, or you have parallel series. They have 4 kinds of feedback. But the most popular, I would say, is this. This is the most popular. Probably I would say, I don't know the percentage, but maybe 80–90% are going to be like series parallel. So this series parallel is also called a voltage feedback. Why is it called voltage feedback? Because the input to the feedback is a voltage, because the VO is applied here, so it's a voltage. And the output of feedback network is also voltage, because this voltage is series with the input voltage. So this is basically voltage and voltage. So it's a series parallel, but both sides are voltage, right? So we call them a voltage feedback. Well, so with the voltage feedback, we can basically write the same equation that we did before. We can quickly write this. So basically, you look at it is VF is all here, VF is here. So VF is beta times VO, and you have from here to here is called VI. So VI equal to VS minus VF. But here, if this is ideal, like op-amp, we don't have current, and then VI is simply VS minus VF. But if it's not ideal, if you have a resistor, then we have to minus the voltage drop on the RS. So here is that we have to minus voltage drop like IS RS. So this term can be neglected if IS is 0, and then this term can be neglected. Can be neglected. Okay. So then our VO is equal to VI times the gain over A. So we can plug in all this number. If we neglect the current, you plug in these 3 numbers, you'll get exactly the same thing as we got before. But that's not the point. The point is that we want to analyze this circuit in like a little more detail. What happens if the input resistance is not 0? What happens if there's current flowing into the amplified network, right? So those are going to give us
a very better understanding in terms when we get into actual circuit. So far, we've been using block diagrams. So now we're getting to a little bit more difficult, getting op-amp. So this is op-amp, and we assume the op-amp does not have current coming in, which basically like the op-amp we had the MOSFETs with differential input, so there's no current coming in, and there's no resistance at the gate, right? So the resistance infinity. So therefore, there's no current. If there's no current over here, we can get the voltage with VO the voltage divider. So we get right away is we get this feedback network means this VF equal to VO divided by R2 plus R1 times R1, which is equal to like R1 over R1 plus R2 times VO. So therefore, all better is, if you look at previous page, what is better? Better is VF over VO. So it's VF over VO. Therefore, we get better equal to R1 divided by R1 plus R2. So that's how you get better. Now you understand. Well, because there's no current, like if there's a current over here, we cannot do this lightly because this current is no longer series. But without that, we have R2 over R1, R1 over R1 plus R2, so we get better. Now, because we can go further down to get the gains, things like that. But I think what we're going to do is we're going to skip that because we have done that before. So now let's move on to like a real example. Instead of using like op-amp idea, now we're going to have this circuit to have a voltage feedback. So when we calculate the beta, we want to know like what is VF over here. So in this case, what happens that when we determine all that thing, we need to short this VS so that we can get better. So we put this like ground, and we put that to ground. There's no voltage like in all these things, so therefore there's no current in this MOSFET. So there's no current here. R2 and R1 become series, and therefore you have VO by dividing between these two, you get VF. So this is the tricky part now. You might say, okay, how do you know there's no current in the MOSFET? I think that's the tricky part. We'll understand a little bit further later. So here basically you have VF equal to R1 over R1 plus R2 over VO. And then we'll have better is VF over VO equal to R1 plus R2. So this is similar to the op-amp that we got before, which is the beta. The next step, of course, is going to get like beta times A, the loop gain. This is the feedback factor. It's going to be a lot more difficult to get loop gain because we cannot basically eliminate this resistance to get the gain because that's not going to be accurate. So we have to leave them in the circuit in order to get the loop gain. Now, there's one thing that I think is interesting to note that if we short the input, and then we apply, let's say we want to apply some sort of voltage across the output. Can we get like the loop gain? Which is impossible because we apply voltage over here. The whole circuit really doesn't work because this is grounded and we always here because some voltage over here. We really don't know how to calculate like the gain of a circuit. So to be fair, it's often difficult to get the loop gain and knowing where to break a circuit to get the loop gain. Remember on the block diagram, I said, okay, cut it anywhere. So in theory, yes, you can cut it anywhere. But in practice, it's very difficult. So, but often, the book gives you one clue that you can cut the circuit somewhere if if the input resistance is infinity. So that's good to cut it. So for this circuit, what we're going to do is we're going to do a little bit later before we actually get in the numerical numbers. But here, we want to verify another thing. If this is a negative feedback, we want to understand if this is going to be a negative feedback. So what happens with feedback? Because so far we've been talking about negative feedback. Like, of course, last week we talked a little bit about the positive feedback to get the oscillation start, right? But with the negative feedback, what it says that if your input increase, your feedback also increase. So therefore, the difference between there and here, they say, what do we amplify the circuit is the difference between VG and VS. So VGS is what we develop, right? So if you still have trouble to understand that, I want to draw the small signal circuit. So for the Q1, the small signal circuit is going to be like, we can draw, well, I guess we can draw either T model or pi model, but in this case, T model is probably going to make more sense because we have R1 and R2 at the source. So let's draw T model. So with the T model, so this is our T model for the for Q1, and you have VS applied to the gate. But remember, there's no current here. So basically, this is VS, and you have 1 over GM at the source, and then R1, R2 will copy it here. So that's you have this RD1, and the output of Q1, which is here, that's called VD1, is supplied to the gate of Q2. So we can draw Q2 because it's a common source. So Q2 is easy to use pi model. So we can do this pi model, which means this is a gate here, and we get this current. And of course, we have to connect this. We have to connect this R2, say R2 to the output, we connect it over here. So now we finished the whole circuit. So this is your like circuit. Now, if you look at here, there actually is one point over here. There's no connection. So this really what tells you that if you know the small signal model, then you see if there's a part of the circuit, there's no electrical connection between the right hand and left hand, this is where you should break the circuit. Okay, so you break the circuit over here, it will make it easy, right? So which means this is where this is between VD1 and VG2. So we break over here. That's why in the book it says break it over here. So we can get the loop again. Now, of course, this circuit, for now, we're not going to get loop again, but what we're talking about is we want to see whether it's negative feedback or positive feedback. So to identify whether it's positive feedback or negative feedback, we simply would apply so we are amplifying VGS, which is VS minus VF. If VS increase, see what happens. Want to understand. So if, let's work together. If VS increase, let's assume that this initially was proportional with VO that has not changed because you have a source and output. So at some moment, we're going to increase VS. So we increase VS, this has not changed, which means VI, which is input between gate and source, is increased, right? So if that VS increase, which means VI increase. If VI increase, means this is GM times VI, or GM times VGS, right? Which means this is going to increase. Okay, so if this increase, which means VD1 increase, negative direction increase. VD1 increase, which means this is GM times VD1, we always going to increase, right? Because this current increase, therefore this will increase. This will increase, which means we have increase. Will increase, this will can increase. So that goes to VI increase, which means VD1, ID1 increases. So ID1 increase, which means VD1 increase. We're talking about absolute value here. So VD1 increase means VD2 increase. VD2 increase means ID2. Actually, not VD2, but ID2 increase. No, not here. ID2 increase means VO increase. So VO increase, which means VF increase. So what we have concluded that if VS increase, will result in VF increase, which means VF increase will make VI less. VI less means, okay, this is going to be less, and this less, this less. So eventually they come to that equilibrium point. So this is a negative feedback. So in the future, if you analyze circuit, anytime if you increase VS, for whatever reason, if VF not increase but decrease, you see what happens? VS increase, VF decrease, which means VI is getting bigger. VI getting bigger means the output going further to that direction. So that's the positive feedback. Okay. So this is example we have, and then let's go. Oops, what did I do? I did it. Okay, simply just okay. So let's move on to see another example. There's another example, and this example is actually simpler than the other one. You see, okay, before I go on, what type of converter is this? What type of amplifier is this? No, the drain has a resistance. Actually, output is at the drain. You see, we always at the drain. We always at the drain. Yeah, it's a common gate. It's a common gate. Okay, so we apply the source input, and then we have gain where output at the drain, and we have this. So this, but this is not very clear because we have feedback over at the gate. So therefore, it's really hard to identify because common gate typically this will be a ground, but we have a feedback. So because the MOSFET does not have any current into the gate, right? So therefore, the feedback over here is simply a voltage divider. So we can easily get beta equal to SM R1 over R1 plus R2. So that's our beta because this current is zero current over here. But you might say, okay, why do you say it's a feedback? Why do you say it's a feedback? How do I know it's a feedback? Well, you see, your input is at the source. And this amplifier, we take output at the drain. What are we amplifying? You remember, the amplification is always done with VGS. In this case, they mark it as VI. So what is VGS in this case? Or VI? Can you get VGS or VI in this case? No, actually VGS is not VI, it's minus VI, right? So minus VGS equal to VI, because VG is over here, VGS, right? So minus VGS equal to VI means VI is positive or negative here, which is VS minus VF. So VS minus VF, right?
So it's VS minus VF. So therefore, it is a feedback because you are taking, you are amplifying not just input, but input minus some sort of VF. And VF is related to VO, so apparently it is feedback. So the next step is we're going to look at whether this is a negative feedback. We're going to see whether it's a negative feedback. So similarly, what we're going to do is we look at what happens when VS increase. Yeah, let's see. If VS increase, how about VI? VI will increase. And VI increase, what happens? The drain current is GM times VGS, right? So the drain current actually increase. So ID increase. So ID increase means your output is ID times RD. So therefore, your output will increase. And that increase means your VF increase. So this is a negative feedback, which means if VS increase, VF increase, then the difference between these two becomes smaller. So your output will now become smaller instead of bigger. So that is a negative feedback. Now, of course, if you don't get this, other way to understand it is to draw the small signal circuit. Okay, once you draw the small signal circuit, you have a much better understanding. Like in this case, we can draw on this corner is that you have, this is on this side. So we're going to draw on this side is G and this S. So all S is connected to VS, and our gate is connected to between these two resistance, R2 and R1, and this is to ground. Okay, this is our VO, and our transistor on the other hand would have a current source, and then connect to RD2 ground, and then here we have VO over here. Yeah, so this is going to be your ground. You see here, we have VGS, basically they mark it up as VI, which is the difference between these two. Okay. Yeah, so actually, no, actually, sorry. VG is correct, and VS is connected to VG. VS, so VG to S, VGS is open. Yeah, so here. Okay, so here's correct. So we're going to have our, yeah, gate and source are connected to this current, controlled current source. But in any case, later on we might have, if we have time, we can go back to see where we can get the loop gain and we get the feedback factor. But here we just want to confirm it's negative voltage feedback. So what are we going to do is, now you see the actual circuit, right? So what we're going to do, we're going to go back to this like block diagram. We're going to do a few things on the diagram, on the block diagram. And then after we got the block diagram working, then we'll go back to those circuits and we're going to revisit them. We're going to do the actual, like how to solve the actual circuit. Because it's easier to look at the block diagram type of write up to make sure that it's mathematically easier to understand. So in this example, what we are doing is the top one is the feedback control circuit, with the feedback network with the basic voltage amplifier, and the input side is the voltage feedback, the output side is the voltage feedback. So this is again the voltage feedback we have. Now,
we want to say that, well, this whole circuit is equivalent to this. And this is input is VF, and the output is VO. Okay, so you might ask, what do you mean? Like, what exactly do you mean, like, by this feedback network? So what we said is that sometimes we need to find out what the feedback network is, what is better, which VF or VO, and sometimes we need to get, again, also the loop gain. So by taking this circuit out, the feedback circuit out of the whole circuit, by applying a voltage at VO and get VF, take the ratio, you'll be able to get better. So that's what really what it says. So when you have an actual circuit, what you need to do is just simply break the whole circuit, apply voltage over here, and get VF over here. So therefore, you will get feedback factor. So this is maybe I want to go back to one of the circuit over here. Like when we said, we get R2 or R1, and I said, well, there's no current here. I mean, ideally, we cannot say there's no current here because as long as there's voltage at here, there might be current over here. So what it does, it says is that we don't care. We will simply take the feedback because this is a feedback circuit. We'll take out the feedback circuit. We'll apply voltage at the feedback side, and we measure the output on in the point we measure the feedback circuit, and then we get the ratio. So basically, in this circuit, what you're doing is we take this. Okay, well, what we are saying is that this is our feedback circuit. Let's put a ground. So let's put a ground. So this is VO coming back, and this is VF. So basically, this is R2, this is R1. So we just take this circuit out. We forget about everything else. Simply get this circuit, apply voltage at the output side, and measure the voltage on the feedback side, and then you get the ratio. That's it. That's how you get better. So this is number one. So this is what we need to do to get it. The next step is that in a lot of applications, we want to find we want to find like the gain in ideal situation. And you guys probably already know that if it's ideal, if it's ideal, which means A is infinity, if A is infinity because AF equal to A over 1 plus beta times A, which means it's going to be A over beta A because A is infinity means 1 is negligible, so you get 1 over beta. So if it's ideal, AF is 1 over beta. So in the problems, often you will say, okay, find the beta value if the circuit has an ideal gain of 10. And you'll say, okay, if it's ideal and the gain is 10, which means beta is 0.1. So it's fairly easy to get the conclusion. But often, as I mentioned before, to find beta times A is very important because often we cannot find A in most electronic circuit. In most feedback circuit, we cannot find the ideal A. So we need to find beta times A. So in order to find beta times A, we need to break the loop, okay? So we break the loop somewhere, and then we apply a voltage, and then we get the measured voltage, and then we get the gain. So now so this case, now we're gonna go back to find where to break. Like in this circuit, guys, remember in the same circuit, we break before Q2. The reason we break before Q2 because that is where actually the two circuit has no electrical connection. So that's good that we break. So which means we'll break it here. We will break it here. Break here means this line is gone. So if this line is gone, we apply voltage of VT over here. Then we measure the voltage VR over here. And then if we measure VR, and then we find VT, so we have VR over VT, and that is our A times beta. So that is our beta times A. So the idea is that we're going to break the circuit over that point. Then we're going to find, we're going to apply VT. We're going to find VR. So this is what we have. Oops. Yeah. Oh, okay. Well, anyway. So this is where we actually break the circuit. As you can see, we break it, we apply VT over here, we measure VR. Now you guys might wonder, like, so this is why the fundamental knowledge we're learning in the past is important. So the book no longer draws the small signal circuit. They assume you guys know how to do it. So they're going to say, okay, we have VT applied. So now we know what ID1, ID2 is. So if we apply VT, do you know what ID2 is, guys? Without joining the small signal current circuit? Or given VT? But Q2 is a common source. VT is equal to VGS. ID2 is equal to GM times, we neglect the RO here. So ID2 is GM times, no, not RD. I'm talking about ID2, not VO. So ID2 is equal to GM times what? Times VGS, right? Remember this? And what is VGS here? VGS is equal to VT. So VGS equal to VT, right? So VGS2, let's call VGS2, which means ID2 is GM times VT. Okay, so now let's calculate VO if we can. So ID2 is the current inside the MOSFET. If we use ID2 times RD2, do we get VO? So this is the question. If we use ID2 times RD2, is that correct? No, why not? Yeah, because ID2 flows between RD2 and also flows here too. So you cannot do that. So which means this equation is not correct. So we need to say this is wrong, okay? So if that's wrong, then how are we going to move forward? Well, you see, RD2 and R2 and R1, really they become like a current divider. So current would flow, some current will flow up, and some current will flow down here, right? So therefore, we would have I1 in this case would be ID2 voltage divider between RD2 plus whatever in this branch. But this branch, well, first of all, we see R2. So which means this R2. Can we simply say R2 plus R1? Can we say that the total resistance is R2 plus R1? Why not? Well, because when the current I1 flows to here, it goes some here, it goes some up. So therefore, we have to consider there's some current going up, some current going down. So we cannot simply add R1, but going up, what is equivalent to this resistance over here? No, it is grounded. This is 1 over GM. This resistance of 1, I will draw the small signal equivalent circuit after I do this, which means it's going to be R1 in parallel with 1 over GM. Okay. Now we got I1. Right? Right. So now I got I1. But what next? The next thing I need to do is I need to get ID1. Because eventually what I wanted to do is VR. Now you can do the other way around too, because we go this because I already know how to do it. If you don't know it,
And you can say, okay, we are, what is we are? We are in this case is ID1 times RD1. Now there's no negative sign. Why? Because ID1 is market going up. It's not going down. Okay, so ID1 going up. Okay, so we get ID1. Now we are is ID1 now, but we don't know ID1 yet. But you see, I1 flows here. We got two branches in parallel. So ID1 is a voltage divider of I1. So therefore, we will have I1, ID1 equal to I1 voltage divider. Voltage divider means this is going to be R1 is at top. It's the other branch resistance. R1 plus 1 over GM. Okay, so now we got it. See what do we have? So we plug in this one to here. Well, actually, yeah. So we plug in ID1, this one here, and then we plug in. Then we plug in I1 back here, and then we get R2 here. We plug in all the way. Every like step, you simplify the number. Now you get VR. VR is equal to ID1 times RD1. So ID1 is this. So it's RD1 times this R1 or R1 plus 1 over GM, and then times I1, right? Times I1. But I1 is this. So I1 is the whole thing. This thing times this thing times I1. But I1 is this. So I'm going to write this back over here. I'm not going to leave the ID2 over there. So it's going to be RD2 over RD2 plus R2 plus R1 in parallel with 1 over GM. Now suppose here is ID2, right? But ID2, we already have equation over here is GM times VGS, which is GM times VT. So then I'm going to replace that ID2. Oops, what happened? Oh, this doesn't work very well. Okay. Something strange happened with my pencil. Anyway, hopefully it'll work. So R1 plus R2 plus R1 in parallel with 1 over GM and times ID2, but ID2 is GM times VT. So now you get this one all written up. So you just divide by VT on both sides. You will get your beta times A equal to VR over VT equal to, yeah, so it's going to be like all this like RD1 times GM times R1 over R1 plus 1 over GM times RD2 over RD2 plus R2 plus R1 parallel with 1 over GM. Okay, so this is quite a long equation, but finally, this is only gain. So it's voltage over voltage. So therefore, one of the things you guys verify your answer is that this has to be unitless. But is it true? Well, this resistance over resistance, okay, good. Resistance over resistance, good ratio. And this resistance times conductance, transconductance, which is also cancelled. So therefore, you do have like unit is like no unit. It's a ratio. So this way we got this loop gain. So, oops, what happened? Oh, I don't understand. Oh, I see. Okay. This is another page. Well, you guys, oh, that's very difficult. You know, I cannot do it by observation, but I think if you do more and more problem, you'll be able to do it. But instead, if you cannot do it, the best way is to draw the small signal circuit, like what we have drawn before. So we're going to repeat it here. The only difference here is going to be we break the circuit. Now actually we have we have also input grounded. So we're going to draw the small signal equivalent circuit. We start from Q1. So Q1, the gate is grounded. And we have this. 1, R2, which will connect to there, and then the gate is grounded, and then we have this going here. We're going to use the T model. Because there's something at the source, we also use T model. The only thing that I think you could be careful is where to measure VR, right? Because we'll have this breakdown circuit. The important thing is that when we break it, we measure VR. You see, VR is at the drain, but the drain has a resistance RD1. So that's why we put the RD1 to ground and we measure VR. So over here, I think you guys will have a much better picture is that because, you know, this is GM times VT is over here, right? So, and then you have current. Oh, I think in the previous slide, I messed up somewhere. I forgot the minus sign because I1, ID2, they have opposite directions, right? So we probably can go back to correct it. So I1 is equal to, so this should be minus sign over here. Yeah, ID2, I1 is ID2 minus sign, and over here ID1, so ID1, and we are ID1, okay. So I think that's what we have is RD1 is minus sign. Let's go to here. So if we do it here, you can see this is the VGS, and so this GM times VT. So you have here is current is ID1. This got ID1. So ID1 you can see is GM times VT. That's what we written from the previous equation here. And then from ID1, you break down to two currents, one flow down here, one flow down here. So this current divider. So I1 equal to ID1 times, so this I1. Again, minus sign. So ID2 plus whatever this whole resistance on this branch. So but that branch Rx, we can find it, it's going to be R2 plus R1 in parallel with 1 over GM. So this is important because what you guys see, because the gate is grounded, so 1 over GM is actually connect to ground. And I1 also connect to ground. So basically, if you look at here, is that this R1 and GM1 is in parallel. So this two in parallel. Parallel, right? And then, and then once you find I1, right, and you can find ID1, which we're putting it in this direction. So ID1 equal to like I1 times R1 plus 1 over GM. So this is what you get ID1. And then we have VR equal to ID1 times RD1, right? So this is exactly the same we got, but this is better to understand which one is which. The only important thing that you have to be careful is that the gate is grounded and there's no current at the gate. So even though the current direction on the up one, like GM times something, but it's actually same as ID1. Now, one of the confusing part, a lot of the time the student confuse that, okay, now my gate is grounded. Why is that my GM, like this one? We know that this is GM times VGS1, right? So my gate is grounded. So why is it my GM times VGS1 0? Why is that current 0? Why is it not an open circuit? Why is it not 0? because you have a VS, right? Even though VG is grounded, VS is not grounded, so VGS is not zero. If VGS is zero, yes, you have zero current. But VGS is not zero, so therefore you don't have zero current. But we don't know that current is, so therefore we simply forget about it. We simply use the voltage divider, current divider to get the current over there. Okay, so here, so we got that. So this example that we can get for that. I think we are going to do. So what I'm going to do today is let's take a quick break, maybe a 10 minutes break. Can come back at 5:10, and I have 2 more examples. That's what I do because the feedback control is very difficult to understand without actual circuit. In the block diagram, it looks nice, mathematically easy, but once you get the circuit, it's so much trouble that you have to understand how to get abelian things like that. So I'm going to go through examples today. And the advantage, of course, you guys know that the exam is very much the examples. Okay, so let's take a break. I know we don't have that many people here, but still, let's take a break. And we're going to continue in a few minutes.
So I was here, so when I have this, I can't do anything over here. You can't type anything in these. So do we have to get spice? Because this is the LT spice.
Well, it should be, it's just a different component.
Or that was just what I was telling you. The only thing we can do is you go here and then you just pick one. And then when you pick one, I'll just say, I pick this one. You still can't change anything.
Okay. Well, I mean, that's fine too. If you,
So just simulate it.
you
like-
simulate and you explain it like why there's difference because of
simulate it like with the ideal one or with you pick one?
anyone.
Either?
Yeah. Yeah. Because ID2 is going down this way. So I1 is going down this way. So which means you have current going this way and current going this way. So basically what you're looking at is this I1 is this way, right? But this is the current going this way. So you see they're both coming out and this ID2 is in this direction. So this is negative.
Is I1 would be this one?
No, I1 is here. This is another current we didn't care. So they only calculate.
Oh, I see, okay.
So I1 is one of the split between, you know, these two added together, it'll give you this idea.
All right, thank you. First one.
Yeah.
This is my L 0.6. Is that like any unit, like 0.6N or
What are you doing for that?
for the calculations for the L, the line?
L.
Yeah.
Oh, L, yeah, L has a unit.
Yeah, so is it what unit? Because it's pretty much based off of the ratio between these two.
Do you know what L is?
Yeah,
What is it?
isn't the length?
Yeah,
Yeah,
length has a unit of length.
but it's based off of the voltage.
Oh, it doesn't matter because you have other units that they're gonna cancel each other. You
Yeah, so
Okay,
I can pick any unit.
no, you cannot.
So what would the unit for L be? If yeah, 0.6.
Well, that's a length unit, length, like micrometers, meters, millimeters,
So this
meters.
would be
Well, you have to find out.
600 meters. Or
600, yeah, 600 meters for
Yeah.
transistor. So
that's pretty big, though.
you have to figure out.
Oh, okay.
You have to figure out. Yeah.
Yeah, because I was like, oh, that's pretty big.
No.
Because I found the ratio,
Okay.
and then yeah, I was just like, okay, I don't know what units this would be.
Yeah, the units it will carry over from other numbers,
Okay.
you know, and then eventually you'll have.
Okay.
Yeah.
Yeah, because I know since L is W over L,
Yeah.
L is kind of the same for every single one, but the ratio would be determined by the width. Okay.
Yeah. Okay. So let's move on. We're gonna have two examples. This one might look familiar to you already. We get use this many times. The reason I bring this one because this is a very confusing way to break the transistor or the amplifier. So apparently to get the feedback factor is easy because again, like what they said, assume the gain is infinity, take out the circuit, apply the input, and get output, and then take a ratio. So in this case, you can see clearly the feedback is R1 over R1 plus R2. So beta is very easy to get. So we can get beta is R1 over plus R2. So that's easy. But how about beta A? I mean, you might say, well, if that amplifier as A, like given a gain of A, you cannot say that the loop gain is better times A because the feedback is going to change the gain actually. So we have to find the gain, loop gain. So in order to find the loop gain, first of all, you assume the infinity, like we get the beta. And secondly, we're going to go to get the equivalent circuit. So assume that this amplifier is not ideal. It has a gain called mu, and I got an input resistance of RID, and we get feedback and so on. So now this is the equivalent circuit. So from this equivalent circuit, we want to find the loop gain beta times A. So the difficulty is that here, is that we can, like in the previous circuit, well, we break at the gate where there's no connection between the right hand and left hand. But in this circuit, the question is that can we break that at like somewhere over there? So the answer is yes, but you have to be careful is that like what the book did was very confusing. So what I want to tell you is that like you have to like maybe put some extra like lines so that you understand what happened. So if we break the circuit between the red and the black, we break it. So now, well, in fact, as a matter of fact, we didn't break anything because there was no connection, right? So what you're talking about break, well, that's how really it works well is that we break it over there. So if we break it over there, what you're doing is you're going to apply a voltage over here. And then because you're breaking that, where do you measure the voltage then? Well, see, we have trouble because are you going to measure the voltage over here? Right? Well, that wouldn't work because you apply VT, then you measure we are basically they're parallel, right? So you see, this is the important thing. When you break it, you have to break it such that you are able to calculate the whole thing. So in this case, what we are doing is instead of breaking over there, what we do is we're going to have to break over here. Okay. So now if we break it over here, the circuit will look like something look like this. Because we break it, so we can remove that connection over here. So this is where we break the circuit. We find the circuit look like this. So here we also have trouble because when we break it here, you see what we're doing is we're going to apply a voltage over here. We apply VT. Then we're going to match VR. But since we broke the circuit, you all of a sudden you say whatever you do over that VT, there's nothing at VR. So apparently this is not true. So what happened is that this is where again it's important because said, well, if you break at somewhere there's resistance, you have to make that resistance unchanged for the original circuit. So what really does it set is that you have to have this resistance here. Didn't change. So you have to have this R ID over here. Yeah, you can break it, but this RID has to be kept in the circuit. So it's like splitting RID into like two identical twins. Okay, one is for the the right hand and one for the left hand. So for the left hand, we apply VT. For the right hand, if we do this, and now it's become much easier because we have like this VT, so we have this mu times Vi, which is mu times VT, and then this current goes here, and then we have current coming this way, then we have current coming this way, and of course this current this way. So basically, you do have like a few resistance changes, like this two are in parallel, and then in series with this one, and then this whole thing is going to divide current with RL, and this RL is going to divide the voltage between RO and the whole stuff. So it's quite a, well, it's not that difficult, but it takes some effort really to find out, you know, what is the voltage. Now, for example, we can do maybe a few steps, like this, the voltage over here, that's called VO. So VO is going to be a voltage divider between RO plus this RL in parallel with whatever this, let's call it RX times RL in parallel with RX, then times mu VT. So you see what it means, that this RL is in parallel with all the rest, right? And that resistance divide the voltage between RO and the whole thing. So now we have VO, now we divide it. So now we can calculate the voltage over here, which called VY. So VY is going to be a voltage divider between this R2, so R1. So between R2 and R1. So this is going to be R1. Now R1 is in parallel with IID. And this is going to be R2 plus R1 in parallel with RID. And that's going to be times VO. So we got VY. And now we can get VR. So VR is going to be, okay, the VIRD actually plus RS. Plus RS. So you see that RID and RS are in series, right? So this in series, and then you parallel with this one, and then plus R2, you know, that's this in series with the whole thing over here. So, and then now we can have VR equal to voltage divider between RRD and then RID plus RS. Okay. So now you see, okay, you got VR, and you plug VI over here, and then you have VO, so you plug VO over here, and then plug VI over here. You see, it's just a bunch of like resistive equations. But once you get that, you get better OA equal to VR over VT. So the only tricky part is why they break it over here. And after breaking, they actually have two resistors. One is for the other side, one is for the other, for this side. So this is a kind of interesting, because in the future, if you do a circuit for, let's say, a BJT, you have R pi, right? So even if you break at that, like input at the gate, at the base, you will have R pi. So you have to put R pi on both right hand and left hand. The one resistor, but on both sides. With MOSFET, it's so much easier because there's no resistance at the gate. So this is what we have for that one. So the next one, we're going to look at a much more complex circuit. Actually, this circuit is a video example in the book, but I thought this would be really good for us to look at, you know, how to get the how to get the beta and how to get the loop gain, beta times A. Now for beta, again, it's easy because if you look at, usually the gain can be found quite easily by just opening the circuit. Now in this circuit, we will assume like the gain is infinity, we take out the feedback. So one thing to notice that there's a resistance over here, but this does this have anything to do with the feedback? Because we always here. So we all, I mean, this current flowing, yes, that's true, but your feedback is right over here. So that's nothing to do. So therefore, we will take this circuit out, we will get the gain, the feedback gain or feedback factor beta to be RS1 or RF plus RS1. So this is the circuit we're going to get the feedback factor. So that one's fairly easy. So the next is really just to get beta A. Now beta A is very complicated. Now what I'm going to do is I'm going to start by doing what we did before, just observing the circuit. And then after that, I'm going to redraw the small signal equivalent circuit so that you see how much easier to do either one. So for this one, apparently we have to break the circuit. Now guys, you don't break in the feedback loop because that's really not easy to do it. So the breaking point is that, as we said, if there's a resistance at somewhere there's like infinite resistance, input resistance, that's where go to break. So in this particular example, we can break at the Q2 or we can break at the Q3, either one, it will be fine. But breaking at the Q2 probably make it a lot easier, a little bit easier than breaking at the Q3. So we're going to break it over here. So when we break it here, we're going to apply voltage and we're going to measure the voltage over here. Okay, so let me erase the whole thing over here. Let's make it a little bit clear. Oh. Okay. What happened? Cancel from start? No. One from start, from current. Okay. Oops. Something happened. Okay, sorry about that. Oops. Okay. Yeah, we can probably from start. It's probably not a big issue. Yeah. Okay. So we want to find beta A. So therefore, we're going to break over here. So after the breaking, we apply voltage or VT to ground. Then we're going to measure VR. So since the circuit is broken over here, we're going to start to look at each step. So let's do it together. You guys are going to be really fluent by this time. Oh, I cannot erase that. Okay, that's fine. So let's do it by step. So let's start with VT. So we apply VT at the Q2. So therefore, we can get the current of Q2. Now remember, there's no current between Q2 drain to Q3, right? So we can easily get the current at Q2. So let's call it ID2. So what is ID2? GM times VT, right? Okay, great. And then we now can get VD2. What is VD2? It's minus ID2 times ID2, right? We get the voltage. Okay, so now we get the voltage at the gate of Q3. So now our output is at the source. So what would you say for Q3? What type of amplifier do you have? Source follower, right? Well, it is source follower, but the problem is that we have resistance at the source. So therefore, we have to, or what I mean is, we have output over here, so you have resist as source, but we also have feedback resistor connected. So therefore, if we don't have RF, it will be fairly easy. Like if no RF, you guys probably can. If no RF, we can get VO right away. You guys get VO. How much is VO? If no RF, suppose. You have current now. Right? So how do you get it? You simply would calculate ID3, right? ID3 is equal to what? Let's say GM3, that one's GM2. GM3 times VD2, right? So we already have VD2. So now if no RF, then our VO will be times RS2, right? So this one, again, I want to highlight this one, just so you guys know that if no RF. But the problem, of course, we do have RF. And what is the connection between RF and RS2? It's kind of in parallel, right? But the problem, of course, is not RF is not in parallel with RS2 because there's something connect over here. Okay, and then can we say that RF is in series with RS1? Can we say that? Can we say RF is in series with RS1, guys? No, because you have current also going up there. So, however, we know when we do this, we always ground the input. So, which means we use the T model. What do you see between gate and this source? 1 OGM, right? So the gate is grounded. So between gate and source, 1 OGM, which means there's like a resistance 1 OGM to ground at this point. So therefore, we would have like resistance is going to be like resistant over here. Let's call it. But okay, so ID3. So we have VO. So VO is going to be ID3 times, which is going to be RS2 in parallel with RF plus RS2 in parallel with 1 OGM, GM1. RS1, yeah. RS1, yeah, RS1. So you got VO. So see, and then once we get VO, now we can get the current, the voltage over here by doing voltage divider between RF and the other two. So let's call this VS1, okay? So VS1. So VS1 is going to be voltage divider, which is VO times voltage divider is going to be it's going to be so the resistance, the voltage divider between this part and this, right? So the numerator is going to be 1 GM in parallel with this one, and the bottom is this. So it's going to be RS1 in parallel with 1 over GM 1 divided by RS1 in parallel with 1 over GM1 plus RF. So we found VS1. And once we found VS1, of course, you can find ID1 or IS1, which is same. So ID1 is GM1 times VGS1. And VGS1 here is going to be VG0, right? So it's going to be just going to be negative like GM1 times VS1, okay? And then, so that's kind of current going down, right? So that's the current going down this way. So now we can calculate VO or VR. What is VR? VR is going to be ID1 times RD1. Don't forget the minus sign, right? Because the current going down this way. So now you see here, we have RF, which is this, and you can plug in VD1 over here to get this one. Now you have VS1. So we're plugging VS1 here. Now you have VO. So we're plugging VO here. Okay, then we have ID3. Now we have ID3, we have ID2. Now we have ID2 over here is given. And then ID2 is a function of ID2. And ID2 is a function of GM2 times VT. So you plug in all this in, you get a relation between VR and VS. So now you get better times A. So yeah, so I got a couple of slides. So now sometimes again, if you're not familiar with kind of looking at the circuit, you can always draw a small signal model. So when you draw a small signal model, it will become much easier to analyze. So let's do that so that you guys can get a better picture of what we're doing. So again, we're going to break it here. So let's break it here. We're going to start with Q1. So Q1 gate is grounded. We're going to use T model because again, this, you know, so this because there's something at the gate at the source. So therefore we're going to use the T model. So ground T model current over here, and then 1 over GN. Okay, now we have these two resistance. One is RS1, and one is F. So, and this is the Q1, but of course at the drain of Q1 we have RD1. So that one is going to be going to ground. RD1. So this is here we have VR. That's where we measure. Here is where we break. VT. Okay, so that's Q1 we finished, and VT also we draw. Now we draw with Q2. You see Q2 is a common source, so therefore it's a very simple circuit with pi model. You want to use T model, fine, but I wouldn't use T model because this is really a common source. So we will use and the drain is connected to RD2. Okay, so now we got Q2. It's very simple. From Q2 gate, from Q2 output to Q3, there's another MOSFET. Apparently, here it's and then this circuit is a common drain, which is source follower. Therefore, you would want to use the T model here. Right? So you can use T model for this one. So again. So this is 1 over GM 3. And this RS2 to ground. And here we go. You see, in the calculation, we didn't count 1 over GM3, but you yeah. So the reason is that because you see that current flows to here, and but we are calculating VO between ground. So whatever you have here, it really doesn't do anything, right? So we're getting the voltage over here. Therefore, which basically what we want you to know is really just the current. Now remember, there's no current between gate and there, right? So even though, so mostly sometimes T model is confusing because there's connection, but that connection is no current. So basically, what you could actually do is you could say, okay, I'm going to just disconnect here. It does not change anything. But the reason you connect it because sometimes we need to know like what is the voltage we need to calculate. If you don't connect, you don't get the voltage at the point, right? So for some calculations, it's a little bit more difficult. So yeah, so basically, you have all this. Now you basically saying, well, with this one, you see what happens over here. So see, this is the interesting part, right? Because over here, this is ground. So basically, by calculating the resistance, what I can do is I can break this one. I can say, well, this is going to be a ground. See, this will make sure that RG1 over GM and RS1 is in parallel, right? But of course, the problem is you really cannot break it. I break it just for you to see, yes, these two are in parallel. Because if you actually break it, the current cannot go through, which is no good. So basically, eventually, here we have to have this connection. But when we break it, we just want to see, okay, this resistance truly they are in parallel because the middle point is the ground. And once you put these two in parallel, you get resistance, and this ground. So this resistance is adding to this one, and this is in parallel with this one, right? And then that's how you get your VO. So, I mean, you're basically doing exactly the same thing. But of course, the way that we get, eventually we have to get VR. So even though, we do all these manipulations like this in parallel, and okay, so the next one is we get, okay, and then this is in series with RF, okay? And then of course, and then this is in parallel with RS2. So that's how you get it. So GM and RS1 in parallel, and then this one is in series with RF. Okay, and then the whole thing over here is in parallel with RS2. Right. So is that simple? If you look at the equivalent circuit, right? So, but again, if you don't draw the equivalent circuit, you can still, by doing observation like what we did from the last slide, that we get that. So I think we're finishing actually a little bit too early. But do you guys have questions on the example? Like, do you guys get a better picture, like how to break it and how to draw the small signal model, how to get the beta times A? Because what you're really doing eventually is you're going to get this beta A equal to VR over VT. Now, once you get VR over VT, is that because we also have beta calculated in this case is R2 over, I mean, in this case is RS1 over RF plus RS1. So therefore, we will have A equal to beta. So this is the key point. I mean, you might say, oh, beta cancel. Yeah, that's right. But we actually don't know A. So therefore, we only know beta A. Like if beta A, let's say, is 10, and beta is 0.1, then you got A is 100, right? So A is 100. Right? So that's how you get it. And once you get this gain, you can see that if once you get A, now we can go back to get like the different gains. Like if it's idea, we can get AF equal to 1 over beta, which in this case, for example, if beta is 0.1, then we get 10. So if beta is 0.1, so we get that. So in ideal case, but if it's a non-idea, then you will get AF equal to, if non-idea, AF will be equal to 8 over 1 plus beta times A. So in this case, you have A is 100, and 1 plus beta is 0.1 times A is 100. So you have 100 over 11, right? Yeah, 11. So this is going to be like 0.998 or something, 99. So not 0.99, sorry. 10.99, 10.9, sorry. and 9.9. So it's going to be 100 over 11. It's going to be like a 9.9. And then this gain typically in the units of volt per volt, it's like a unit less, right? So now if people are saying, okay, well, if I know better is 0.1, I got 9.9. But what happens if I want the gain F to be exactly 10 in non-ideal cases? What can you do? So if I want AF to be exactly 10 for non-ideal case, what can you do? So typically, you see the way that we find the loop gain, is going to be like, it doesn't change basically because the circuit parameter fixed. Of course, if we change the feedback resistance, the gain will change a little bit, but you'll find it's not much. Okay, it's going to change. Yeah, it's going to change. So if we want to get the gain to be exactly 10 for the non-ideal case, if you can go back to the equation saying, well, I know that AF is going to be A over 1 plus beta times A, and I found A is going to be 100. So this is going to be beta times 100. And that's, I'm going to put this to be exactly 10. See what I get is I have 1 beta times 100 equal to 10. Okay, so 10 times, yeah. So in this case, I have beta equal to 9 over 100. So I have beta equal to 0.9. So if I have beta equal to 0.9, I can go back to what is beta? Well, beta equal to RS1 over RF plus RS1. So RS1 is given at 200. So you have 200 over RF plus 200 equal to 0.9. So now you can calculate RF to be like 200 divided by 0.9 minus 200. So that gives you sort of, is it true? 0.09. 0.09. That's what I want. It can be 0.9. So 200 divided by 0.09 divided by minus 200. Like if this is 0.1, no. Beta is, no, beta is 0. Beta, no, sorry, I made a mistake here. Let's redo it. So beta is, AF is 10. Was A 100? Let's redo it. Sorry. So this, I think this part is probably important. You guys might see this. Beta, we found A is beta A equal to 10. Okay. So we said beta times A equal to 10. So beta A is 100. Well, basic example is not very good because this beta wouldn't have to be 100. I mean, A shouldn't be 100. Typically, because you got a like 3-stage amplifier. Like the last stage is 1. So first stage would be say 20 times 20 will be about 400 at least, 500 maybe to 1,000. But anyway, so let's assume A is 100. So let's assume A is 100, and so AF is A over 1 plus beta times A. So it's going to be, we want F to be 10. So F to be 10 means 10 over plus 1 plus beta 100 equal to 100. So beta times 100 equal to 10 minus 1 equal to 9. So beta is equal to 9 over 100. So it is 0.09. Okay, so if it's 0.09, which means we're going to have this RF. RS we have beta equal to RS1 or RS1 plus RF. So therefore, this is going to be equal to RS1 is 200 is given, and then 200 plus RF equal to 0.09. And we can say that 200 plus RF equal to 200 over 0.09. So, okay, so RF equal to 200 over 0.09 minus 200. Yeah, you get some sort of number. So RF would be a quite large number, I would say, in the kiloohms. Well, which is true because like 0.1, if 0.1, this 200, this would be 2K. Yeah, so that's okay, that's correct. So it'll be 2 point some kiloohms to get actually better to be 0.09. Then you got to get to be loop gain to be closed loop gain to be 10. So this is very important. I think we probably can go back to one of the things that we look at here. I want to see here. Okay, so in the by the end of the chapter, we probably already forget is one is the sensitivity, and the other is the bandwidth. So those equations that we derived in terms of sensitivity, we got it right over here. Do you guys like the sensitivity? If I ask you, if A change say 20%, how much AF change? So basically, if this is 20%, and if beta times A is a certain number, like in the case we had was 10, which means your sensitivity reduced by 10 times. If beta times A is 100, you reduce your sensitivity by like 100%, almost like 99%. So this is good. And then for the bandwidth, for high frequency and low frequency, basically remember that the high frequency pole is increased by this much, but the low frequency pole is reduced by a factor of this much, right? So I think we did that equation as well. Yeah, so the low frequency pole, they're reduced by this much. So what we're doing is right now is we just simply try to go from both block diagram, like we get all these numbers, and we go to the actual circuit. Now one of the things that we found, okay, yeah, so I want to look, yeah, this is what I want to come back, is that we did look at the high frequency, but if you look at the low frequency, if you draw the whole picture, you're going to see this, like the high frequency we got here. But if you look at the low frequency, and the whole thing, it's going to extend. So this is the high frequency pole. And this is WFH, this is WFH, this is WFP. So you see, this whole thing was expanded, but the gain, of course, is reduced. And you know that the gain reduced by A over 1 plus A beta, and this was decreased by 1 over 1 plus A beta, and this was increased by 1 plus beta times A. So everything was like related to 1 plus beta times A. So this is very, very important. And once we understand all this, what we're going to do is next week, not next week, you guys have a break, but when we come back, we are going to move on to talk about, I mentioned about the different feedback, like voltage, current, voltage, current. So there are 4 types of feedback. So we're going to look at each one of them and how you can find out the gain, the bandwidth, and all that kind of stuff. Now, of course, we're also going to look at what happens if you have like non-idea amplifier on the top. Like in the one that we have example so far, we have the gate resistance 0, which I mean, or infinity, which is a MOSFET. But you have a BJT, the input resistance is R pi, it's not 0, right? So what we're going to do with that? And if we also have output resistance, you know, what are going to do, right? So we're going to derive some simplified method to eventually, what we're going to do is over here, the whole thing over here is going to be equivalent to like AF. Or VS or VI, whatever that is called. So basically you see this output VO is going to be VS times AF. And so we want to find AF in all like non-ideal situations. Because electronic circuit, really nothing is ideal. Now often we talk about ideal case, which means we assume the idea, we get some like a top high level observation or understanding of the circuit. But in reality, nothing is ideal. So we will have to go really talk about what happens with an idea. And then when we got to circuit like this, we can still do it. But sometimes if the circuit gets really complex, like 3, 4, 5 stage amplifier, and the feedback is not simply a voltage, maybe a current, how would you do it? So we're going to actually get all those done. And I think it will really, it becomes really interesting. But yeah, so I think I'm going to stop here because it's probably going to be too much if I move on. But yeah, the week after the break, you guys come back, we're going to have a quiz pretty much covered what we covered, you know, so far today. And probably more, you know, some on the block diagram type 1 plus beta 8, you know, what does it do to the gain, to the middle band gain, to the low frequency pole, to the high frequency pole, to the sensitivity, things like that. And then probably you're going to look at, you know, some of the circuit, if you break it, you know, how do you get the beta and how do you get the loop gain? So things like that. Okay, so my iPad is low power. Okay. Any questions? No? Okay, well, with that, okay, good. I really appreciate you guys staying here. Otherwise, I'll be lecturing to a ghost room. But yeah, enjoy, and I'll see you in 2 weeks. If you guys have questions, I'm here, even though it's a break. So I'll be answering my emails. So if you guys need something, let me know.